Hey, what's going on, everyone? In today's video, I want to discuss how to plot a Fourier transform. And the reason I want to go over this topic is because it's an interview question that I really like to ask to incoming entry-level candidates, especially ones that say they have experience with image or signal processing. And the reason I like this interview question is because it's a very simple question that can be answered very quickly, but in order to answer it correctly, they really need to have a good grasp of the fundamental concepts behind Fourier transforms and those kind of topics. While this question is pretty straightforward, there are several common pitfalls that many people run into. And in this video, I want to go over what some of those pitfalls are, then at the end, go over how to correctly generate one of these plots. All right, so now let's kind of act out how this interview question would go. So the first thing I would do is show the person a plot like this. So here we have two signals. We have just a 10 hertz sine wave and a 100 hertz sine wave. And then on this bottom plot here, this is just the sum of the two signals added together. And the question will first be, can you just give me a rough sketch of what the Fourier transform of this signal would look like? And if the person has a basic understanding of Fourier transforms, the sketch they will give will usually look something like this. It'll basically be on one axis, the horizontal axis, they'll have frequency in hertz, and then the y-axis will just be some kind of scaled frequency response typically. And they'll show some spike at 10 hertz and some spike at 100 hertz. And this is because, our signal only has those two frequencies. It's made of a signal that's purely 10 hertz and a signal that's purely 100 hertz. So we should have two spikes there, and everywhere else should be zero. And if they paid close attention to detail to the amplitude of the signals, they might notice that the 10 hertz signal actually has a bigger amplitude than the 100 hertz signal, and so they might draw these two spikes at different heights. But that's kind of a small detail that if they didn't pick up on, I wouldn't hold against them or anything like that. Now, assuming the sketch that they draw is mostly correct, the next part of the question I'll ask is, given you have any programming language you like, how would you write the code to generate the plot of the Fourier transform? And usually people who have, signal or image processing on their resume are usually doing this kind of stuff in like Python or MATLAB or something like that. So yeah, so I'll ask, okay, what code would you write to generate this plot? And the typical response people will give is they'll say, well, in the software development environment I like, there's just a built-in Fourier transform function for that. And so I say, okay, show me how you would use that built-in function to generate this plot. And I'm going to show you the pseudocode of what a typical answer would be that runs into several of these pitfalls I mentioned earlier in the video. Here's an example of what someone might write to generate the plot of a Fourier transform that would be incorrect. Here I'm working in Python, and I'm just using NumPy to do the Fourier transform and matplotlib to do the plotting. Suppose that this lowercase variable x represents the signal we're looking at, this 10 plus 100 hertz signal down here. And so the candidate might say, okay, well, I'm going to generate the Fourier transform first by using NumPy's built-in Fourier transform function. So they pass in the signal, then they get out the Fourier transform, which I'm just calling capital X. And then they just call plot. They just plot the direct output of the Fourier transform. Even before they show me the plot, I can already sort of probe into several things that are wrong here that I'll ask them about. The first thing I'll ask here is I'll say, okay, let's go back to the sketch we had. And you said there would be a spike at 10 hertz and 100 hertz. Well, how far does this actual frequency axis go? Does this go to 200 hertz? Does it go to 1,000 hertz? How far is it going to go? Because in the code you've specified, there's no variables describing frequency. And it's pretty common when you're doing a plot, like any kind of 2D plot, you usually say something like plot some xy pairs, right? And the x pairs are the values of your horizontal axis and the y's are the values of your vertical axis. But in this case, they've just plotted the output of the Fourier transform directly. And so what Python or MATLAB will do just by default is that if you don't give it this x variable, it's just going to basically use the indices of this array as the values on the horizontal axis. And the indices of the array have nothing to do with um, the actual frequencies of our signal. So that's sort of the first pitfall that people run into, is they don't create a proper frequency vector to use as their horizontal axis. The second main issue here is that the output of the Fourier transform, each element in this vector is a complex number. So, and this will change depending on programming language, but what exactly is going to happen when you just start plotting complex numbers, right? Because, in the sketch we were working with, we have, this is a two-dimensional sketch, there's an x and a y variable, but a complex number is already two-dimensional, right? So we have a frequency axis for the horizontal, but then we have the real and imaginary components here. What's going to happen with plotting all those complex values? How are we going to just put that into a single axis? So that's the next thing I would ask, how are you going to resolve how to display these complex numbers properly? So now with those issues out of the way, let's actually look at what would this code generate in Python. And this is the plot for it. So here's our plot. We do have we have two pairs of two spikes. So we have something kind of like what we expected in the sketch. But let's look at where they are. So we have this first spike at what looks like around, say, 5, and we have the second spike at around, say, 50 that kind of goes up and down here. And then there's a mirrored pair over here. So this is what you would actually get from running this code. And so here I would, ask, okay, so what is this spike at 5? What is this spike at, 50? Why is this first one smaller than the second one? And why is there sort of like a mirrored pair over here? From the beginning of the interview question, we kind of established that, okay, this is kind of what we're expecting. And now we've got this. So what happened here? Now let's go over the correct way to generate this plot. And the first thing we need to do, even before writing any other code, is we need one more additional piece of information. And I didn't initially provide this in the question, but to anyone who has a good concrete understanding of this topic, they'll know to ask for this piece of information because it's super important to actually do this correctly. And that piece of information is what is your sampling frequency? How many samples per second are you using to generate these different signals of 10 hertz and 100 hertz? And that's because of the Nyquist criteria. The Nyquist criteria says for whatever the highest frequency in your signal is, you need to sample at least double that frequency. So for example, here our highest frequency in our signal is 100 hertz. So that means we need to sample at least 200 hertz. And that also means since our sampling frequency is at 1000 hertz, that means the highest frequency we could possibly detect is a 500 hertz component in our signal. So our final Fourier transform should have a horizontal axis like this one that should go from 0 to 500 hertz because our sampling frequency is at 1000 hertz, and because of the Nyquist criteria, we shouldn't be able to detect anything higher than 500 hertz. Before we start writing the code to correctly generate the plot, there's one last thing I want to discuss, and that is I want to go back to that plot we had where we incorrectly plotted the Fourier transform, and I just want to go over this horizontal axis one more time. So this 0 right here, this still does correspond to 0 hertz. And then, like we said earlier, the highest frequency we could possibly detect if sampling at 1000 hertz is a 500 hertz component. So this value in the middle actually corresponds to 500 hertz. And then the value at the far end of your Fourier transform, this always corresponds to your sampling frequency itself. So even though you can't actually detect a 1000 hertz component when sampling at 1000 hertz, you're still going to have this mathematical artifact here that's going to be a mirror image of your actual frequency components on the left side. And if you were to keep generating a Fourier transform sort of indefinitely across the horizontal axis from like 0 to infinity hertz, you would keep seeing this pattern repeating at intervals of your sampling frequency itself. So here it's at 0 hertz, then it repeats at 1000 hertz, it'll repeat again at 2000 hertz, 3000 hertz, and so on. And again, that's just sort of the periodic nature of the mathematics behind the Fourier transform. All right, now let's go over how to correctly generate the plot. The code will start off similar to the previous incorrect method. First, we're just going to pass our signal into the built-in Fourier transform function, and we're going to get an output of Fourier transform. And again, these are all going to be complex numbers. Next, we need to deal with the fact that these are complex numbers. So we didn't, explicitly state this before, but usually when you say you want a plot of a Fourier transform, you usually want the magnitude response. Every now and then you might be interested in the phase, but typically we assume we're talking about the magnitude response. So in order to get the magnitude of every single element in this array, we just need to compute the absolute value of it. And that'll take all of these complex numbers and convert them to real values by taking the absolute value. So now we have this variable here, which I'm just calling, the Fourier transform's magnitude. And one thing I'm going to do just for plotting purposes is I'm going to scale this by the maximum value here. So I'm just going to take every value in our magnitude response to the Fourier transform and divide it by the maximum value in that array. And what this will do is it'll just take the biggest value in the array and map it to 1, and then scale everything down accordingly. This just makes the plotting a lot nicer and easier to understand because there aren't really intuitive units on the output of doing this absolute value and the output of the Fourier transform itself. The next thing we need to do is create a vector of frequencies to plot on our horizontal axis. Remember, that was one of the issues last time, was that we didn't have any sort of, like frequency variable here. We just directly plotted the Fourier transform. The frequencies that will be on our Fourier transform, like we mentioned earlier, is that this value at the far end corresponds to 0 hertz, and then the value at the far right should correspond to our sampling frequency, which is 1000 hertz. So we're going to want to make a vector that starts at 0 and goes to our sampling frequency of 1000 hertz. And we just want that to be as many elements as the output of our Fourier transform itself. Now we can just plot these two vectors together. We can plot the vector of frequencies we have and the scaled magnitude response of the Fourier transform. So we have the frequencies, we have the Fourier transform values now that are all magnitudes, so they're all real numbers. And we just want to now restrict our plotting window. We don't want to plot from 0 to 1000 hertz because this isn't really data of interest to us. This is just a mirrored, artifact of this data. We really just want to plot from 0 to the highest frequency we can detect, which is 500 hertz over here. So the last thing we're going to do is just limit what our x-axis is going to be. Instead of going from 0 to our sampling frequency, we just want to go from 0 to half of our sampling frequency. And so when we run this code and follow these extra steps, we should get a plot like this. So now we have a correct frequency axis that goes from 0 to 500 hertz. And when we look at where these spikes are, we have a big spike at, and my cursor's, it's pretty hard to align it perfectly, but looks like this is around 10. And then when we look at this other peak, it is around 100. And also the 100 is about half the size of the 10 hertz component. And again, that's because the amplitude is actually twice as big for the 10 hertz signal than the 100 hertz signal. Now we can put the generated plot we have here right next to the sketch we did earlier, and we can see they look pretty similar. Everything's not exactly to scale, but we can have a lot of confidence now that our plot is generating the thing we expect. And there we have it. Now we have a generated plot that matches the sketch we initially drew earlier. For anyone who's studying, signal or image processing in college right now, or they're trying to brush up on some of these concepts for an interview coming up, I hope this video was able to help refresh some of your knowledge on Fourier transforms and how to correctly plot them.